Welcome to the new chapter in CMPE59G neural networking course. Today's lecture will be given by Can Gürsoy from the WE department at Mosque University. Can is working with Professor Ali Emre Pusani in the WE department, and today's lecture will be about representing the whole information as the whole frame represented within a single molecule, what we call molecule as a frame. So the floor is yours.
Thank you very much, Professor Tugcu. I'm Can Gürsoy, a master's student in WE department, advised by Professor Pusani, kind of co-advised by Professor Tugcu. So my topic of presentation today is modulations and frame-based approaches for molecular communications. I tried to make it as more lecture-like as I can. So here we go. Okay, so molecular communications, as you have probably discussed way too many times as of now, is a communication scheme for communicating at the nanoscale. We have many different versions of molecular communication, maybe calcium signaling, or molecular motors, what have you. But today we're going to specifically focus on communications via diffusion. So when we're trying to communicate via diffusion, we have pretty short ranges on the order of a couple of micrometers, maybe a couple of tens of micrometers at best, and pretty low data rates actually, like maybe a couple of bits per second or maybe even less, like seconds per bit maybe. So to accomplish this, but of course, like we have many different possibilities, many different biological applications, even with this data rate, of course. So that is why we're working on it, right? So the message is encoded in the messenger molecules, some physical property of it, may it be quantity, type, or the position in a. So we can use the molecule axis, which corresponds to the frequency actually in traditional EM communications, pretty much, not exactly. Quantity as in amplitude, or time of release as in time of release in EM communications. So we can also use some combination of these three, or maybe come up with another way, as we will talk about later on. Anyways, so the channel response for a three-dimensional single transmitter, single receiver molecular communication via diffusion channel is kind of like this, actually. So we have a distance of d between the closest point of the receiver node to the release point of the transmitter, and we have the receiver node with a radius of r sub r. So when we have this scenario, we have an interesting curve actually that has a heavy right tail. This is a big problem for us, considering the fact that we're trying to communicate as fast as possible. The amount of molecules, the amount of molecule probability in the tail distribution, if you will, actually hinders us from the opportunity to push our boundaries and go higher in terms of communications. As you can see, even this simulation was done with d equals 5 micrometers and rr equals 5 micrometers. So the range is pretty short. And even with that, actually, the arrival probability is on the order of seconds, actually. Generally speaking, we have megabits per second data rate in EM communications, or cable communications. But here we have a lot less. Okay, so the fraction of arriving molecules until time ts being the symboling interval, whatever modulation we have, is given by this formula. And using this formula actually corresponds to, corresponds to the integral of this curve from point 0 to some ts in the time axis. So, okay, so to find the channel coefficients, FIR channel coefficients or IR, whatever, they can be found by actually differentiating the 2 points. For example, if we have a symbol duration of 0.5 seconds, the first first channel coefficient is the area under this curve, up to point 0.5. The second one is actually this area, so we can find it by subtracting the expression at Ts equals 1 from Ts equals 0.5, so on and so forth. So anyway, what this gives is actually the probability of a single molecule arriving at the receiver in a certain period of time. But this is for a single molecule, right? And this is a Bernoulli experiment, pretty much. So we have a Bernoulli experiment with success probability P, and when we transmit n molecules, then the amount of molecules that arrive at the receiver in that region is actually binomial distributed with MF is, we will talk about what MF is later on, but it generally represents the amount of molecules that you transmit per transmission. Whatever transmission you have, whether you have a concentration-based one or a molecule-based one, the number of molecules and the pK. Okay, so about the modulations. About the modulations, so the most generically used and the most maybe the simplest one, and maybe the most easily implementable one is CSK, concentration shift keying. And of course the most primitive version of it is binary CSK, binary concentration shift keying. To accomplish this, we actually send n molecules to represent a 1, and a 0 molecule signal is transmitted, so a no signal is transmitted to represent a bit transmission of 0. Of course we can make a ternary transmission modulation scheme to account for no communications as well, but we can always use some pilot symbols and like inform the receiver that we're starting the communication. So this is generally the way to go in the literature, and this is also called on-off keying. So on for signal transmission, off for 0 transmission, pretty much. The problem is actually this thing unfortunately faces a severe amount of ISI, intersymbol interference, meaning the more ones we send, the more molecules we dope the channel with. And the problem with this is actually the molecules start to accumulate in the channel, and as a result, we actually have these residual molecules corresponding to earlier 1 transmissions that can screw up our communication big time, actually. This is a big deal, and it hinders the communication really big, I guess. Okay. As another modulation, we have a binary Mosque, B-Mosque. And for this, we have, for 1, we send type A molecules, and for 0, we send type B molecules. And of course, we need to transmit n over 2 to normalize in terms of the total amount of molecules we send, because of fairness in comparison. Anyway, so this is another way to go. For detection, we do maximum detection. So the receiver receives in every time slot, the receiver receives the amount of molecules of type A and type B and counts them both and says, hey, A is higher this time, so okay, I got a 1, or B is higher, I got a 0. As another one, we have a binary pulse position modulation, and in pulse position modulation, position-based modulations in general, we divide the time slot into 2 or more, and in the subslot, so we have the first subslot and the second subslot in a bit slot, we release the molecules in the first slot or the second slot. At the receiver end, we do maximum detection among subslots. So mind you, we can always have higher orders of these modulations. For example, if we have more than 2 molecules, 2 types of molecules, we can make Q-Mosque and carry multiple bits inside of a single molecule, which we'll be talking about later on. Or if we have multiple thresholds, we can actually send multiple bits via a single concentration signal, or the same thing may apply for the pulse position modulation as well. Anyway, so we have a higher level modulation of MCSK now. MCSK is essentially a CSK modulation, but with a twist. For odd time slots, for example, for the first time slot, the 3rd, 5th, 7th, 9th, whatever, we send type A molecules, n of them if we're going to transmit a 1, 0 of them if we're going to transmit a 0, and for even time slots, we do the same thing for B-type molecules. And the thing is, the receiver only listens to A-type arrivals, for example, for the odd times, and the receiver only listens to the B-type arrivals for even time slots. So detection is, of course, for odd time slots comparison with the threshold of tau, of course, for type A molecules this time, and for the even time slots for type B molecules. So this is another way of using the two molecule types differently, right? So in terms of encoding the information in the type of the molecules, we actually generate these orthogonal channels, if you will, and make the receiver listen to the first channel in the first time slot, second channel in the second time slot, first channel again in the third time slot, and so on. So by doing this, actually, we're extending the channel response so that even we conserve our bit rate, we can actually face considerably less ISI. So it's a really good thing. So. But the thing is, the original MCSK paper actually does this, but we can actually further improve this by extending the listening period from, for example, we can listen to type A in the first time slot until the third time slot comes, right? So we can also count and listen to type A molecules in the transmission period of B. Of course, given that we have synchronization between a transmitter and receiver. When we do this, we actually get a stronger signal, which corresponds to actually having less noise, less variance in the number of received molecules. So So we'll have a better performance overall. This is called DMOSC in the literature, but I'm going to refer to MCSK and DMOSC as the same thing because they're extensions of each other pretty much. So note that if we have access to more molecules, we can increase the cycle size, right? If we have four molecules, we can do this for 4. If we have 8, we can do this for 8. So if we can synthesize these molecules, or if we have them in our pools of messenger molecules, we can actually increase the cycle size, reducing the ISI even further. Okay, so our focus is type modulations, basically. I'm sure you've seen this figure quite a lot as of now. This is actually 4-Mosque or Q-Mosque. This has 2 bit slots, if you will. You can change it by placing a fluorine or a hydrogen atom in this carbon chain in these 2 slots, and whatever you have, whatever molecule you have, will correspond to a different molecule. In this case, hydrogen corresponds to 0, fluorine corresponds to a 1. So this is how Mosque works, and this is 4-Mosque. So basically, Mosque uses the internal chemical structure of a messenger molecule. And this is a really good concept, actually. So this is a small molecule, right? But we have DNA molecules. We have amino acid chains, more complex sugars, for example. So we can use more complex molecules, bigger molecules, and embed even more information there. And this is a big possibility because these molecules are, the channel response is pretty much given to us. Well, of course, like the bigger the molecule gets, a slightly slower diffusion it does. But the thing is, if we are able to encode more and more information in a single frame, single molecule in this case, we can actually carry this information, and at the receiver end, we can actually surpass the bad channel behavior, if you will. So, of course, this molecule is a hydrofluorocarbon, and the problem with this is actually it's highly flammable and it's explosive, as far as I know. So, in another paper in the literature, people actually introduced isomers of glucose or 6-carbon sugars as messenger molecules. 6 carbon sugars have this 1 carbon head, 1 carbon tail, and 4 carbon worth of information bits we can encode in. So we can actually have 16 Mosque, for example, inside. And the family is called an aldohexose family. So yeah, this is it, I guess. Well, of course, you need to have a certain header and a certain footer for the receiver to differentiate between the beginning of the message and the end of the message as well. So this is the header and the footer are characterized by the regions in purple and yellow in this case. So okay, generally speaking, we have a structure like this, right? We have a header, we have a footer, and we have all these bit slots that we can encode our message in. So think of these as slots. These can be the hydrogen or fluorine small bonds over there. These can also be nucleotides. These can also be small amino acids, what have you. So whatever molecule you have, whatever biochemical molecule you have that you can use, you can actually have this. So the overall structure looks like this, and we're going to look at things from a communications engineering perspective to this thing, pretty much. So what we in our research propose is actually we can use the available bits differently. In terms of only using these for information embedding, we can actually encode a complete data frame, having sequence numbers or frame identifiers, pretty much, and an information-bearing payload. So the frame size is n throughout this presentation, and the frame identifier bits, number of frame identifier bits are called BF, and the information-bearing payload length is called BI. So the sum of them gives us n, pretty much. I'm sorry. So okay, frames are represented with molecules. That's a really big thing. So these are molecules, and they also exhibit Brownian motion, right? They have their diffusion coefficients. They have their Stokes radii. So they do the random walk that regular other molecules do. So like Mosque, the system synthesizes, transmits multiple replicas, MF, number of multiple replicas in this case, of the same frame molecule. So the ideal case, think of an ideal case where we have perfect frame identification. Whatever molecule we transmit, we know exactly the transmission instant of the molecule. So we have this date and time and whatever we have. So we have exact knowledge on when we send the signal. When the receiver gets these, when these molecules arrive at the receiver can actually perfectly decode the time and rearrange them in the correct order and say that, oh, this message was that. This is excellent. And the only probability of error in this case is if none of these MF molecules that we transmitted have arrived at the receiver, right? So we send MF molecules. They were arriving with a probability P1. So this is the expression. Unfortunately, of course, this is not the case in like many cases in engineering. And n is a finite resource. And as engineers, of course, we need to use our finite resource to optimize for our purpose, whatever that purpose is. We'll talk about it later on. And since n is a finite resource, our best case is actually having a so since we have a limited number of sequence numbers, we need to cyclically reuse these numbers, right? So we have, I don't know, we have 16 numbers. So we start with 1, 2, 3, 4, 14, 15, 16. And in the end, we start with 1 again. And of course, the problem is, this introduces an ISI to the system, intersymbol interference, like the case in concentration shifting, like the case in Mosque. Mind you, it's a lot less, we will see it later, but it still has ISI. So the frames from earlier frame transmissions with the sequence number 1 can interfere with other frame molecules in the channel that are transmitted later on with the same sequence number of 1, because we have to cyclically reuse these numbers. They can overlap on top of each other, and the receiver may actually decode wrong information because of this. Okay. So of course, the more frame identifier bits we have, the longer the cycle is. So the lower ISI we face. This is a very good thing. So for a fixed bit rate of TB, we have a frame duration, frame rate of BI times TB. What am I talking about now? So the thing is, we have two constraints in any communication channel pretty much. Our constraint 1 is the rate of the communication, and our constraint 2 is the energy budget of the communication. And we have to normalize our scenarios in such a way that we, so for fair comparison, we have to normalize our bit rate, and we have to normalize our transmission power to actually make a fair comparison. Yeah. So for a fixed rate of TB, we have BI bits inside a certain frame. So we can send these frames with TF equals BI times TB times in between, right? So higher the BI is, higher the frame duration can be. So okay, remember, this is for every frame though. We have frame identifier bits, and 2 to the power of bf of them. Remember, we have a bf number of frame identifiers, and these bf identifier bits correspond to 2 to the power bf different sequence numbers. So these sequence numbers have a cycle size of 2 to the power of bf, which we can actually cyclically use as I talked about before. So combining the knowledge here, tf equals bin times tb, and the fact that we can cyclically reuse it, the receiver can actually listen to, like in a DMOS case or like in an MCSK case, actually, the receiver can listen to the frame with a sequence number of 1 until the other frame of sequence number 1 is transmitted. This is a very good thing, and it exponentially increases our effective frame duration. In this case, we call this an effective frame duration, and it helps us immensely in terms of ISI reduction. So in terms of only using this part, we're actually using we're using a sequence. We're using 4 times TF in this case, since we have 4 sequence numbers. So in this case, we have two frame identifier bits, and so we have a cycle size of 4. I'm sorry. So we have a cycle size of 4, and we can utilize the cycle size of 4 by the method I told you before, by increasing the effective frame duration and combating ISI. Okay. So we have another constraint. Remember, so we had the data rate and we had the power. We had the energy budget. So in molecular communication systems, the energy budget is actually the energy to synthesize the molecules. Because of that, our second constraint is on the number of transmitted frame replicas, because the molecules in our case are frame molecules, right? So the larger amount of them that we want to transmit, the higher amount of them that we want to transmit, the more energy we need to waste, or the more energy we need to synthesize them, actually. So okay, in a molecular communication system, transmission power is proportional to the number of transmitted molecules, as I said before. But transmitting a larger number of molecules helps us a lot in terms of having a less noisy signal. Because of the nature of the signal, the variance of the signal actually decreases. The relative variance of the signal decreases with increasing number of transmitted molecules. So if we send more molecules, we have a less noisy signal, as a rule of thumb. But of course, we need to normalize this per bit as well. We had a fixed bit rate, remember? So we're going to have a fixed number of a fixed number of molecules that we can transmit per bit, which is denoted by m in this case. Of course, we have bi number of bits inside our frame, and bi number of bits, bi number of information bits in our frame. So we have bi number of information bits and a molecule per bit constraint of m. So mf becomes bi times m. In this case, where, of course, m is the number of frame replicas transmitted per bit. Okay, so this is the key point of molecule as a frame. This is the key point of my research, I guess, on this topic. Higher the BF is, remember BF is the number of frame transmission, frame identifier bits. Longer the overhead is, longer the frame identifier bit part is, we have better ISI combating. But the problem is, higher the BF, lower the BI. So we have a lower number of transmitted molecules per frame in this case. So on one side, we have increased noise by increasing BF, and on the other side, we have severely decreasing ISI with increasing BF. So this is the main trade-off in a molecule as a frame system, which of course tells us there should be an optimum allocation in terms of BI and BF to minimize the error rate among frames, error and erasure rate among frames. Just note that if we send too few amount of frame molecules, if that frame molecule, since they move in random motion, if they go away, if they don't go towards the receiver, if they go astray, then we're actually left with no frame molecule. So this is an erasure, basically. All the information content inside is gone, pretty much. So we can either make errors due to transmissions before, or we can make erasures, actually, because no frame molecules actually arrived at the receiver. So combining them, we have come up with a metric called the frame error and erasure rate, FAR, and there should be an optimum throughput, a BFBI allocation, that minimizes this, we theorized. And voila, there is, of course. The x-axis is the BF axis, and the y-axis is the frame error rate axis in the semi-log in a log scale. So we have a frame size of 15. So we have 15 nucleotides, for example, or 15 amino acid particles, amino acid blocks, or 15 slots, basically, that we can encode our message in. And we have an M value of 3, and we have a TB value of 100. Mind you, generally, TB is on the order of 200 milliseconds, 300 milliseconds on regular concentration-based molecular communication systems. So this is really promising, actually. A system that yields 10 to the minus 5 error probability while communicating at 10 milliseconds data rate, it's actually really good. And of course, this comes as a cost of complexity due to the frame molecules. Anyway, so the existence of a trade-off is confirmed, as you can see. We have a reliable communications at 100 bits per second. Actually, if we have more, bits that we can encode our message in, then we can actually communicate a lot faster, maybe 1 millisecond, maybe even more. So the rightmost point in this curve, the rightmost point is here. I'm sorry, the leftmost point, this is reverse, I'm sorry. The leftmost point receives severe ISI. Remember, BF is the thing that combats the interference, combats the fact that the other interfering molecules comes to the receiver as well. So the more BF we have, the better our ISI combat is. So this case is the case with no ISI, the rightmost point. But the problem is we have a fixed M, so we have a very low number of transmitted molecules on this side, a higher number of transmitted molecules on this side, but a severe ISI situation on that side as well. So combining the two, we can actually come up with an optimal point, and as you can see, we have a reliable communication there. Okay, so note that we have two normalizations, M and TB. TB is a data rate. Of course, like we can change the data rate, increase it if we can, or decrease it if we have a system with a, I don't know, a higher distance maybe. But M and TB are the two normalization variables that we have. We have to obey the constraints of them. So we thought we would try out this molecule as a frame scheme under different TB situations to examine the system, what happens to the system, what happens to the equilibrium, what happens to the optimum point, what happens to the error rate at the optimum point, so on and so forth. So in this case, we have 13 bits inside of our frame. We have an M value of 3 and a TB of 10 milliseconds, 40, 70, and 100. So in this case, as you can see, of course, naturally, as TB goes higher, the communication performance gets better. But the thing is, it converges to a certain point, because after a certain point, of course, combating ISI even more is useless, because the channel is cleaned, I guess. So as we can see, the equilibrium point, actually, the optimal point shifts to the left, because as TB increases, the need to combat ISI, it actually decreases. Because we have the system with these constraints already has a better ISI combating scenario. So we need less BF molecules, less number of bits inside our frame to allocate for the frame identification part. So because of that, the equilibrium shifts to the left. Of course, we can use these extra BF, so trying to decrease ISI even further is not that beneficial, but having more BI and transmitting more, being able to transmit more frame replicas are really good in terms of noise combating. So this is what we got. Okay, so for varying M, this is the other, I'm sorry. For varying M, when we look at the curves for varying M, we have a fixed bit duration now and a fixed frame length, and the varying M values, M constraint values. And the interesting thing is actually the communication, of course, it gets better as M goes higher because our budget is higher. Our budget, our power, so we can associate more power with our signal, which makes them less noisy, much less noisy. So as M goes higher, of course, naturally, the communication gets better. But the more interesting part is actually the optimality holds if you change M. This is an interesting property, and it's really good for power adjustment. So if the nanomachines, since these nanomachines are working in the nanoscale and they're a few micrometers big, they need every source of energy, they need to conserve every source of energy they have. So in the scenarios of low energy budgets, we can actually, of course, considering the communication scenario as well, we can actually adjust the power without losing optimality, and we know that we're in the optimal position again. Of course, it's going to change the bit error rate, but we will know that we're working at the optimum point, so we don't have to recalculate the system again to come up with a new optimum point and trying to operate there and find a new protocol between a transmitter and receiver. So this is a pretty good property of a MAF system. And at the optimum point, just note that I've taken the points in the optimum point and plotted them, and this is what we end up with. So the curve is a straight line, and for the people that are not really familiar with the digital communications engineering world here, if the curve goes straight down, this corresponds to the case that we have no error floor. An error floor is a follow the thing. It's like this. So it has a certain floor, and the error rate can't go even below even we increase the power so much, we can actually help the error rate a little bit after a certain point. That is an error floor, and that is due to interference. Whenever there's an interference, there's an error floor. And in this case, the curve goes straight down, which suggests that actually ISI is negligibly low when we're operating at the optimum point. So since we use our frame identifiers cyclically, if we have enough of them, actually we can, while conserving our bitrate, remember, and while conserving our already high bitrate, we can actually make the frames see a better channel, see a much better channel, and combat ISI, and have this beautiful curve. Like we have 10 to the minus 8 frame error rate, even when we have an M of 5 molecules per bit, which is insane, actually, for a molecular communication channel. Okay. So, what happens with distance? Communication distance, remember we talked about it in the beginning. The communication distance is a key issue in molecular communications. It's low, and it limits our ability to actually convey information to the receivers farther away from us. And the higher this distance d is, the problem is remember the channel response like this. It was like this. The farther away you get, it actually goes like this. and like this, and like this. The signal, the overall signal, the area under gets attenuated more and more. And the problem is the peak goes to the right side as well. So the problem becomes you need to communicate at much slower rates, much slower rates, to actually have a remotely reliable communication when you're trying to communicate at a distance. So this is the main problem of distance in molecular communication via diffusion. This is the physical nature of the channel is the main source of the limited bit rate we can get, and the limited reliability we can get if we try to extend the range of the communication. So recall that the communication channel model is this. So we have D, the distance between the closest point of the receiver to the transmitter, and RR, the receiver. So we define another metric here, R0, which is the sum of these two variables, and it's the point to center distance between the transmitter and the receiver. So okay, of course, when we go farther away, the reliability of the communication decreases. Remember, we're still working on the same constraints that we're already doing. So this was our original case that we talked about before, when R0 equals 10. So the point to center distance is 10, and the receiver has a radius of 5 micrometers. So it's pretty close. It's not that close for a molecular communications channel, but it's pretty close. So if you go farther away, with these, of course, constraints, the channel actually, and remember, BF goes, notice BF goes at the optimal point, of course. The BF goes towards right a little bit. This actually says we need to wait more. We actually need to wait more to combat the additional ISI we get from the distance, pretty much. Okay. Anyway, again I took the points of the optimal point and did this analysis on the scheme before. And the thing is, optimality still holds, remember. Optimality still holds for changing m. So we can safely say that we're working on the optimal point when we do this at a certain n and a certain tb. So the good thing is still the curve is still flat. The curve is still a straight line. So we're still combating ISI pretty well here. But the best part is actually, because of the fact that optimality still holds, a molecule as a frame still has a solution. Of course, it's not ideal. We need to transmit more frame replicas to ensure more of them reach the receiver. But we actually have a solution to increase communication distance. We can simply increase the power, if we have the budget, of course. We can simply increase the power. Of course, this results in a higher energy consumption. But as you can see, with m equals 18, and remember, this corresponds to around transmitting 150 or something molecules per frame. So 150 molecules is still not that large, believe me. And we can actually obtain 10 to the minus 4 error probabilities. And this is, as far as I remember correctly, at a distance of 30 micrometers. So the distance, the effective distance of the communication increased threefold. Of course, at a cost of a certain power, but it's still pretty good. Okay. So up to now, we've seen that a molecule's inner structure can be utilized as a communication frame. And we know there's an optimum, we have seen there's an optimum throughput between BF and BI and for every molecule as a frame system. And a molecule as a frame system, because of these BFs, because of these frame identifier bits, it's robust to ISI, so it's able to yield high data rates with low error rate, or we can actually and of course, comma, with low power and everything, at the cost of course, complexity, and something we'll talk later on. So okay, let's take a break. So this is what we came up to now. We have a channel with certain constraints. We have a really ugly channel actually, and using the inner structure of the molecule as a frame, and combating ISI and combating the noise that the signal generally faces, and finding the optimum allocation, optimum point in between, we can actually combat both of these things pretty well and come up with a good system, come up with a system that yields high data rates with low error rate, which may actually be the future of this thing. So up to now, we have discussed about the possibility of encoding information as a frame inside the molecule's inner structure. By doing so, we have seen that there's an optimum throughput between BF, the frame identifier bits, and BI, the information bits, for every molecule as a frame system. Mind you that this optimum point may be in some scenarios located on the extreme ends, but generally speaking, it's somewhere in the middle. Anyway, molecule as a frame with its BF frame identifier bits, it's robust to ISI, so it's able to yield high data rates with low error rate. So we have other two modulations actually that are quite popular that use the differentiation between multiple molecules, which are named Mosque and MCSK. We've talked about them in the beginning actually. Recall that MOSK or Mosque, the binary version of it at least, has two types of molecules, and for 1 we transmit type A, and for 0 we transmit type B, and we do maximum detection at the receiver end. Well, you can actually extend the scenario to n, whatever number of molecules we have, and actually encode log 2 the number of different molecules we have, bits inside. So in this case, we have, applying this knowledge to a molecule as a frame system, we have a frame with n number of bits inside. So this n number of bits inside, if we allocate all the bits towards information bearing, then we actually have BF equals 0. This is a special case, and this corresponds to actually having 2 to the power n NRI Mosque, MOSK. So what I'm saying is actually we have n different bits, so essentially 2 to the power n different types of molecules, and we can actually assign 10-bit information strings to each one of these 2 to the power n molecules, and this is exactly what 2 to the power n MOSK is. On the other extreme end, BF equals n is also a special case. BF equals n, what is BF equals n? It is actually the case where we use all the different bits inside the frame towards frame identification, right? So if we have, I don't know, 5 bits, we have a cycle size of 32. But what now? We have a 5-bit system, and we've used all 5 molecules towards frame sequencing, and we have no molecule and no bit slot inside to encode our information, so we rely on quantity modulation. And this is exactly what actually MCSK with a cycle size of 2 to the power n does, or more accurately DMOSK in this case, but we're using the two terms interchangeably, remember. So actually performing quantity modulation with by using all bits as frame identifier bits is 2 to the power n cycle sized MCSK. So we can think of this molecule as a frame from a modulation perspective, of course. We're not looking at the things from a modulation perspective rather than a frame perspective. We're looking at things from a communication frame perspective. But actually, when we look at it from the modulation world, it can be seen as actually an optimization between MCSK and MOSK. So we have these two very powerful modulations, but what we do is actually, given that we have enough resources to do so, we're actually optimizing between the two modulations and receiving much better error rates than the other one. That is actually the whole point of the story in terms of modulations, of course. So yeah, remember that MOSK uses more molecules because it's over here, because this place corresponds to having few BF, so more BI corresponding to a higher MF. so we have higher signal power here. We have a stronger signal here, but we have intersymbol interference, a severe one, and which causes a very high error rate actually. On the other hand, we have a very ISI-free channel, let's put it that way, but we're transmitting with only m equals 3 molecules because every transmission has only one bit inside. So to conserve our power constraint, actually, we have to transmit with 3 molecules only. So that is why the error rate goes higher in this region, and that is why the error rate goes higher, and the reason before was explained this region. So we have an optimization in between. So the moral of the story is MOF outperforms both modulations by finding the optimal allocation between these 2 modulations. So BF and BI allocation actually also represents the trade-off between MCSK and MOSK in this case, or DMOSK and Mosque as well. So it can also be thought of as an optimal compromise between Mosque and MCSK, as I said before. So this is very good. This is very nice up to now. We have low error rates. We have high communication rate at the cost of a delay, a latency, if you will. But what about degradation? These molecules are biological molecules, right? They're projected to operate in our bodies. In our bodies, actually, these molecules also have enzymes that break them, roaming around in our bloodstream or in the interstitial fluid, whatever this communication is taking place. So degradation may be a thing because of the enzymes around in the communication channel. So when we send these frame molecules may actually meet these enzyme molecules and they get degraded. For example, if we have RNA, we can actually have RNA esterase, right? It was. So if we have, I don't know, an amino acid chain, there are enzymes that break down those as well. Break those down as well. So since we're communicating with really exponentially increasing the effective frame duration with the help of frame identifier bits, we're actually letting the molecules stay in the channel for a long time. That is how we combat ISI. But from another perspective, when degradation comes into place, these molecules may actually degrade before reaching the receiver, which may actually attenuate our receipt signal at the receiver end by a large margin. This is a possible problem for a molecule as a frame system. So the problem becomes, what if the messenger molecules degrade before arriving at the receiver? Generally speaking, in the presence of enzymes that break the messenger molecules down, if we have enough enzymes in the environment, the decay of these messenger molecules, the chain reaction of them actually becomes one-sided instead of a chemical equilibrium, and the decay of these messenger molecules are exponential with half-life lambda 1/2. So the molecules in the channel, after they're released from the transmitter side, they're actually exposed to this exponential decay. So in order for the molecule to survive, in order for the molecule to be absorbed by the receiver, the molecule needs to satisfy 2 conditions. A, arrival to the receiver, which is denoted by event A here, and B, not being degraded in the meantime. So it needs to survive and arrive at the receiver as well. So these events are independent to each other statistically. So we can actually multiply their probability density functions and integrate them to find the actual survival plus arrival situation, the probability of it. Okay, so what happens if we apply this to molecule as a frame system? So we did that, and we saw 3 regions. Actually, we can separate the exponential decay profile into 3 different sub-profiles. Let's put it that way. So we have extremely fast decays, which are on the order of milliseconds, for example. Like you transmit the molecules, you put the molecules in the channel, and they get immediately decomposed into other molecules. Fast decay with half-life that is comparable to the effective frame duration that we're working, and a slow decay that is which implies, I guess, the half-life is much larger than the effective frame duration that we're working with. So in the case, of course, this is a really cluttered graph, but the bold curve represents the no degradation case in this case. And if the degradation is extremely severe, actually, half of in the top curve, actually, half of the molecules degrade in 1/4 of a second. Actually, it's just really fast. It's actually maybe unrealistically fast, actually. Even in those scenarios, actually, a molecule as a frame still, the scheme actually still holds a certain level of reliability, I guess. But of course, if it goes even higher, like extremely, ultra high, then we may actually see worse error cases. But the thing becomes, the achievable information rate is still much higher than regular modulations, actually. We have to mention that as well. So after the extreme case, actually, if we start to increase the half-life of the molecules, this is the curve corresponding to 1 second half-life. So it starts to go a little bit lower. And for the 4-second curve, it's actually even better than no degradation. Because the thing is, when the degradation profile acts on the interferer molecules more than your own molecules, actually it kills off intersymbol interference even more. It helps you, but it doesn't attenuate your signal as much. So we see the degradation profile with a half-life of 4 seconds being actually better than the original case without degradation. And then when the degradation profile gets slower and slower, the case actually starts to converge to the original curve without degradation. Of course, this is a really cluttered image, so I actually got the frame error rate at the optimal allocation point for different degradation profiles with different half-lives. So as you can see, for extreme degradation profiles, we have this worse error profile, I guess, worse error rate. Then it gets even better. It gets better as the decay is getting slower. You can actually, if you can engineer this, you can actually enhance the performance of any molecular communication system. Including molecule as a frame in this case. And after after a certain value of λ1/2, I guess, then the system starts to converge to the no degradation case. Realistically speaking, for example, for the insulin molecule in blood, I've checked the half-life of it, and it's around 4 minutes, which is like 240 seconds. So it's around like this. For our communications purposes, it's not really even comparable. So we can actually assume no degradation safely, I guess. Okay, so degradation was a really big question mark towards the functionality of a molecule as a frame system. But as you can see, if it's not extreme, if it's not super extreme, then we're fine. Okay, what about multiple receiver systems? Whole point of this course is nano networks, right? So we're trying to interconnect multiple nano machines to each other instead of actually working on a single link. Fortunately, molecule as a frame systems inherently have a possibility for receiver-specific information transmission. I guess I forgot to put that word there. By actually doing something similar to a destination addressing. Okay, so let's think about this scenario. We have 1 transmitter and 4 receivers around, and different information is to be transferred to different receivers. So it's not a broadcast channel by any means. It's not a regular TV channel. It's a channel that is trying to communicate different information to different nano machines. So for this case, molecule as a frame can implement destination addressing depending on the type of the molecule as a frame molecule that we're using. It can be a separate unit attached to a frame molecule. For example, if it's an amino acid chain, we can actually add another amino acid chain, or 2 amino acid chains in this case, to represent the 2-bit destination address for these 4 receivers. Or maybe, if that is not possible, if we have another type of molecule that prohibits that, we can actually allocate some bits inside the frame for that. So the question becomes, should receivers absorb or reflect the molecules sent to other receivers. So I'm trying to communicate with one of you guys, but my molecules are going to other people as well, right? Because the channel is a fluidic channel. The motion is Brownian motion, so the molecules go everywhere. So should you steal my molecules that I'm trying to send to O's right here? So absorbing, like you absorbing the molecules actually helps ISI because I'm trying to communicate with O's, but the molecules going from Basri, right? From Basri to O's, actually they're stray molecules and they are generally ISI molecules, right? Because ISI molecules tend to take longer paths and they take longer time to reach the receiver. So by Basri absorbing the molecules that I'm trying to send to O's, it actually helps the channel in terms of ISI. But of course, it steals some molecules from the channel. Now some of my molecules that I'm trying to send O's, Basri has it, and the molecules are they're removed from the channel. Now, I can't use it for communication. So reflecting does the opposite. It actually bounces the molecules towards those a little bit, but it adds ISI a little bit. But it actually helps the total number of molecules increase. That, of course, I'm talking about my link with O's right here. So for TS equals 200 milliseconds, the coefficients, remember the probabilities of arrival in different time slots, actually become for one receiver it's this, and for 4 receivers that are absorbing, the like other 3 receivers absorbing my links molecules, I guess, it actually P1 decreases. Remember, P1 is the general signal strength that we have in our intended symbol. It decreases a little bit, but just observe, P2 decreases by a bigger margin actually. So the ratios P1 over P2, P1 over P3, and P1 over P4 are much better now. The channel profile, the channel becomes more and more like a one-tap, single-tap channel, an ISI-free channel, if you will. Of course, like it's not free in this case, but the ratio is around 2.5 here, I guess, and the ratio is around 3.5 or 4 here. I mean the ratio between P1 and P2. And in the reflecting case, we have a higher number of molecules, higher possibility of a molecule, higher probability of it arriving to the single link eventually, but we have ISI worse in this scenario. So actually in a CSK scenario, in a concentration shift keying scenario with using these channel coefficients, we actually have this. We have a single receiver scenario right here in the middle. The reflecting receiver scenario is slightly worse, but the absorbing receiver scenario is much better, as you can see. This is pretty good, actually. This is good for CSK. This is good for multiple receivers, nano communications if you're trying to do it with CSK, I guess. But for a molecule as a frame system, actually absorbing receivers are not that good because we're already combating ISI pretty effectively with our frame identifier bits. So we don't need the further ISI combating of absorbing interferer receivers. What we can do is actually we can use the extra molecules that reflecting receivers give us and combat the ISI with our frame identifier bits and actually get slightly better error rates than the single receiver case. As you can see, since the overall power we have, since the overall signal strength we have decreases with absorbing interferer receivers, we have a higher error rate there. For the reflecting one, we have it even lower than a single receiver case in this case. So because molecule as a frame already fights ISI by itself, reflecting is better in this case. So what we need to do for 4 receivers, for this 4 receiver scenario is actually equip every single receiver with their corresponding destination address receptor, I guess, and only when the appropriate molecule arrives at that receiver, we should accept it. Otherwise, it should stay in the channel because I'm going to use it later on for my decoding. I need that signal strength, pretty much. Okay, so molecule as a frame and temperature fluctuations. We're living in a world where temperature actually fluctuates a little bit. Even when the weather report says it's like 15 degrees outside, it's not like that every time of the day, right? So, I was going to put a reference there, I'm sorry. So human body and the external world is subject to temperature fluctuations. And the Gaussian, they found that it's Gaussian distributed around the mean. Like, so when you say it's like 15 degrees outside, it's 15 plus or minus some standard deviation, and it's a Gaussian distribution. So I've tried this, of course, having the human body in mind. I've tried it with the mean 310 Kelvin, which is 37 degrees Celsius, which is a normal human body temperature, with a standard deviation of 25 Kelvin, which is exaggerated, of course, because like if we have, I don't know, 295 Kelvin body temperature, we'll freeze to death, pretty much. But even with a higher deviation, we've actually seen that the deviation does not worsen our error performance that much, which is very nice, because maybe there are some scenarios where standard deviation may go up that high. Some application of molecular communication. Even in that case, molecule as a frame still works pretty good, actually. And of course, it's the same system with different parameters. I'm sorry, same parameters. Yes, so overall, we've talked about a system named molecule as a frame that uses the inner structure of a molecule. And we've seen that it provides actually really exciting opportunities for the molecular communication world. So first of them is, of course, faster communication links, because the channel response hinders us from going faster and faster. But by actually encoding more information in a single molecule, we can actually circumvent that problem a little bit and achieve higher data rates. Low error rates in these high data rates, which is very nice. Increased range, given that we're able to transmit more molecules, of course. Multiple user support, and resistance to environment effects like degradation and temperature fluctuation, and etc. With the cost of course, receiver detection delay. Remember, we're counting until the other frame with the same sequence number comes. So we need to delay our decoding of the frame until the other frame with the same sequence number comes. So we're actually postponing our decision a little bit to actually collect more molecules from the channel as much as we can. So you can't play Counter-Strike with this, but in its region of, I guess, in its region of application, it's still pretty good. And of course, the need to synthesize the molecule. So we're trying to encode the bits inside the molecule, and maybe the best supportive research to this work would be actually finding a way to manipulate DNA molecules or synthesize amino acid chains effectively enough that we can use this in the communication. So this may be a bottleneck. So we're finding the communication theoretic optimal point here, but this may actually be a bottleneck there may actually be a bottleneck due to molecular synthesizing techniques and its speed. So another future work would be actually incorporating error control coding inside the frame, because the bits inside the frames, if the frame is decoded perfectly, all the bits are assumed to be decoded perfectly. But remember, DNA replication is an erroneous process. So while actually in our bodies now, when our cells are replicating, when the DNA material, the genetic material is being replicated, sometimes actually, these are called indel errors. Sometimes you insert another nucleotide in your intended string, or sometimes you forget to put an intended one. So insertion, this is called insertion deletion error, indel for short. So there's this, or there may be substitution errors as well. So you want to, I don't know, put adenine somewhere, but you put cytosine, I guess. So if you do that, that's an error in the bit level. That's an error inside the frame, and I think it should be addressed as a future work, I guess. And I think the problem will become even more interesting, given that we have a small number of bits inside our frame. So we have to allocate it in such a way that we can maybe we should protect the error unequally. For example, maybe we should invest more for the reliability of the frame identifier bits in order for the frame not to be mixed with another frame, because an error in the frame identifier bits is different from another error from the information bit string. So there are many different problems here waiting to be solved. So this. Okay, thank you very much.